Good morning, good afternoon, good evening, everyone. This is Kiran Minnasandram, the Chief Technology Officer for Full Stack Cloud Business at Wipro Technologies. In today's talk, let's traverse through what I call as three eras of databases. Yesterday, where we all started with very simple flat file systems and evolved to, let's say, on-premise relational databases all the way down to today, where cloud databases, NoSQL databases, and real time processing have taken really center stage. And tomorrow, where a lot of significantly advanced AI driven autonomous databases, multi model databases, edge computing are shaping the future. From time memorial, they've always held a whole lot of information, including medical records, purchase history, financial transactions, social media content, so on and so forth. Let's embark on a journey through time exploring the evolution of databases from their inception to where it is today to what really lies ahead of us. So let's straight dive into the past and start the journey from the origin of databases. Sort of in the early days of data management, we fundamentally relied on flat file systems, simple files that were very straightforward, but unfortunately very inefficient for complex querying, complex data processing. Imagine having separate lists for cost for customers and orders, but needing a significantly efficient way to match them. The search, the sort, the update operations could have been much more convenient and time consuming. Thanks to the work by E.F. Cord at IBM during the 1970s, the model of organizing data into tables made it much easier to manage. SQL became the language to interact with the databases, allowed us to efficiently perform complex operations on large data sets. Let's reflect on some of the significant challenges though faced with the yesterday's era of databases. Data redundancy is one significant challenge. How did multiple versions of the same data in different places always led to confusion and errors? Scalability was another challenge. What were some of the financial planning implications of having to deal with increased demand? And of course, without compromising performance, without compromising on the cost spend. Data recovery, security, and complexity of managing multiple relationships in relational databases. This needed some form of very specialized knowledge and skills that to manage the databases. So let's leave yesterday where it was. Let's look at what's really coming up in today's databases. As we sort of move into the later half of the 20th century or 21st century, let's say, one of the notable advancements is the rise of cloud databases. Platforms like Yugabyte, AWS RDS, Azure SQL, Google SQL have truly revolutionized the way we manage data by offering significantly massive distribution, highly scalable, and global configurations. Let me call upon Yugabyte in particular, a high performance cloud native distributed SQL that offers extreme scalability and global distribution, but also provides significant consistency and resilience, making it an excellent choice for databases, excellent choice for businesses of all sizes and scales. This platform provides services that allows businesses to scale their databases up and down quickly, depending on their needs, and additionally offer global distribution capabilities. What does it really mean for managing data? It means that I can access the data from anywhere, from any device, and manage the data, providing an extremely high level of flexibility and accessibility that was previously unimaginable. Let's move on from the relational side into the NoSQL databases. NoSQL databases like MongoDB, Cassandra, and so a host of others. These databases are designed to handle, they're engineered to handle different data types, but offer significantly high scalability than conventional relational databases. And it is quite proven in the world. NoSQL databases are well suited for handling large volumes of unstructured data, examples of social media posts, a lot of sensor data, multimedia content, video files, etc., etc. They provide a more flexible data model, which allows for storing and retrieving data that does not fit into any form of a fixed schema, making them an excellent choice for application that requires, I would say, high flexibility of data schemas, data management. Let's bring in a third dimension to today's databases, real-time processing. I think this is where we have seen over the last, I would say, about 5 to 7 years, significant improvement and significant advancements in data processing. Engines like Kafka or Redis offer very high throughput and very high real-time data processing capabilities, allowing businesses to analyze and act on their data as and when it is generated. And this is very much needed in several industries, be it in the world of manufacturing, be it in the airline industry, be it in the medical industry, in financial trading industries, where ultra low latency is the order of the hour. It becomes all the more critical to manage data at real time, process data at real time, store data at real time. And this is where timely decision making is critical. And as I said, financial trading, online gaming, emergency response systems are a number of different examples one can think of. So, in conclusion of today's databases, marked by significant advancements in cloud computing, real time processing, and the convergence of OLTP and OLAP, I think has evolved quite a bit from where it all started many, many years ago. And as we continue to generate and consume more data than ever, these technologies will be very, very crucial in helping business manage the data effectively and make more informed decisions. I think let's jump to the most important topic that I really wanted to cover is tomorrow. So, as we look towards what's happening in the world of tomorrow, we can anticipate several key trends that's shaping the landscape. One of the most exciting developments is the rise of AI driven, artificial intelligence driven autonomous databases. Again, not to say that it doesn't exist today, the possibilities, the advancement, the profoundness, and the complexity of managing, be it self driven databases, self healing databases, or self intelligent databases, is what's going to come. What it means that these databases can self repair, self optimize, self secure, manage the storage autonomously, and also start to derive results based on the computation that's happening, make it much more personalized in the world of experiences, thereby minimizing the need for human intervention. So for a second, let's imagine a database that can autonomically identify and fix issues even before they happen, optimize the performance to handle peak workloads, and secure against potential threats. Imagine a database that can optimize the storage and computing needs autonomously without any human intervention and eliminate the need for any downtime. And this is the future of AI driven autonomous databases, and the promise will profoundly impact how we manage and maintain our databases. So that's my number one. Number two is the evolution of multi-model databases. Multi-model databases have been around for a while, but there are lots and lots of challenges with respect to mixing relational database structures with non-relational database structures. These are single solution that's effectively or efficiently handle multiple databases and different workloads. For example, traditional databases were designed to handle specific data types, specific workloads, and often requiring businesses to use multiple databases as their demands grew, as the businesses became much more diverse in nature. Again, let me call upon Yugabyte here, for instance, is a high performance cloud native SQL database that provides a unified platform for handling multiple data models and truly making it very easy for businesses to manage the data in a much more streamlined and efficient manner. Multimodal database address this needs by providing a single platform to handle both OLTP workloads on one side, but also OLAP workloads on the other side. That is another evolving feature, and it is going to get much more profound, just like the artificial intelligence capabilities on the databases. Let's talk about the third dimension that I'm foreseeing as a significant advancement that's going to come. That's data at the edges. And this is going to shape the future of databases, especially with the rise of IoT devices and the increased need for real time processing. The demand for storing and processing data closer to where the data is generated is going to get even more profound than what's happening today. Take an example, the cars that we use, the autonomous cars that we see on the road, there's data being generated at the edges. The ability to process them at real time, at the edges, in the ecosystem of several other autonomous engines that are running, needs both compute and storage at the edges. The need to reduce the latency of sending data back and forth and process them at the edge, leading to faster decision making and drive better experiences, is critical. Especially as IoT devices continue to proliferate and the need for real time processing grows, we expect to see much more solutions. So we expect to see more and more solutions enabling data storage and data processing at the edges. And think of this term when you think of edge databases. Don't take data to compute, take compute to where the data is. I think that's going to be the drive of tomorrow. Additionally, combine the power of data at the edges with that of multimodal databases. And that's going to create new possibilities and infinite opportunities for multiple industries. No tomorrow is going to be complete if I do not speak about privacy and security. This will continue to remain top priorities in the future of databases, especially with growing concerns over data privacy and increased sophistication of cyber attacks. There is an even more need for advanced security solutions. Think of homographic encryptions. Technologies like homographic encryption, which allows operations on encrypted data without decrypting, is going to become mainstream. And this is really going to change the way databases are going to evolve in future. Combine this with the edge databases, the globally distributed databases, the power of encryption and the power of advanced privacy and security is going to become even more critical, and it's going to evolve significantly. And this is going to enable businesses to analyze and share the data while keeping it secure and addressing one of the most significant challenges in today's data-driven world. From the perspective of tomorrow's database, let's also look at the data in the post-digital world. We went through this whole digital transformation of the databases, so on and so forth in the digital world. Now let's talk about a scenario, what's going to happen in the post-digital world. Data growth at global scale. Data is no longer going to get confined to a single silo or within an organization. It's going to be an ecosystem play. There's going to be data, there's going to be distribution across geographies, across different departments, across different processes, across different customer touchpoints, across different partners. This kind of data proliferation across globally scalable systems is no longer a nice to have. It's a reality. And enterprises are challenged with the situation. Unable to predict the scaling needs and ahead of time would mean that data management systems cannot always be prepared, but must be elastic. Systems must be elastic. Compute systems must be elastic. Data processing systems must be elastic. Storage must be elastic. Security capabilities must be elastic. However, unfortunately, the elastic scale and database management systems never combine well in a single sentence. Let me repeat. Elastic scale and database management systems are never well combined in a single sentence. It is a challenge for us to handle. Let's talk of, from the world of scalability, let's talk of the physical worlds and the edge computing. And the reason why this is very important is there is significantly blurring of boundaries between physical and digital worlds. Thanks to IoT and Internet of Things and industrial IoT devices, especially the devices around augmented realities, virtual realities, and several of those edge devices that are now becoming significantly compute intensive, but also equally powerful. These challenges are linked to scalability, but they're not limited to it. Data latency at the physical location edges is a very important thing, but the other ability to store and process billions of events from these devices while generating data insights needs closed loop systems. And that is going to be another challenge that we will have to solve for. Let's talk of real-time data processing for a second. Businesses must make sense of real-time data. Databases is going to play an essential role in the ability to process data quickly, and prepare itself for decision making. Real-time data processing requires scalable databases that provides extremely low latency in many scenarios, access to data, but at the same time provide high throughput and seamless integration with real-time technologies, be it real-time streaming, be it real-time compute, be it real-time encryption, decryption, so on and so forth. Databases now will have to play a significant part in managing that requirement. Lastly, let's talk about machine learning and AI, because there's no topic that's immune to machine learning and AI, especially with prediction, classification, segmentation, correlation. There's lots of machine learning type workloads that involves significantly complex data processing, querying, and data transformations. Databases must support intricate queries for, let's say, feature engineering, model training, or model analysis. Be it in the area of segmentation, be it in the area of classification, be it in the area of correlation, regression, so on and so forth. There are many models that the database will have to support. And hence, AI ML applications require real-time data access. And this real-time data access must be provided at ultra low latency speeds for better decision making. And that is critical. Now, all this is not going to be without challenges. And let's talk of some of the challenges. And let me start with some of the scaling challenges. Scaling database is a complex task. We have all dealt with databases for many years. Scaling databases is not adding more CPUs, it's not adding more storage. It's primarily complex owing to the intricacies of distributing stateful systems. The database is a stateful system end of the day. Unlike a stateless world or a stateless workloads, the state makes it incredibly complicated to scale databases. The storage locations, access to computing locations, further exacerbate this challenge. Data consistency, ensuring data consistency across distributed systems is complex and intricate, especially when multiple copies of the same data exist. Synchronization becomes a challenge. A one-way synchronization is one form of a challenge, but a dual synchronization where there are two different systems claiming to be the source of truth, a dual-sided synchronization becomes all the more challenging. So data consistency is while we have done a lot of work around data consistency, I think the future is going to be around how are we going to ensure consistency of data at any point, at anywhere, given the global distribution of databases. Let's talk of the other one that's going to get even more complex and even more challenging is query performance. Think of all the earlier advancement that I spoke about: artificial intelligence, autonomous databases, data at the edges, data processing at real time, multi-model databases mixing both structured data and unstructured data. The querying engine, the query performance, as the data volume grows, the query performance will continue to be degraded. So optimizing queries across distributed databases becomes an all the more bigger challenge. For instance, operational reports for an e-commerce systems using distributed databases makes it difficult to query multiple database instances to obtain accurate reports to accurate data. This is going to be another challenge that we will have to deal with. Let's talk about data movement as a third challenge. Transferring data between databases or replicating data across different distributed systems can lead to synchronization issues, can lead to consistency issues, can lead to data losses. And this in itself is going to pose a significant challenge when we talk of distributed databases or geographically distributed databases. Ensuring consistency is absolutely critical. Data partitioning can be the fourth challenge. Large databases may outgrow in a single server, necessitating data partitioning and sharding across multiple servers. It's great. However, this introduces data management and querying complexities, especially large scale internet facing systems. Let's say, for example, log analytical systems or social media platforms. Partitioning data across multiple servers to ensure scalability and efficient access is not an easy task. Managing a partitioned database is significantly more complex than managing a single database system. Now let's move from the data side of complexity to some of the operational complexity. Managing and maintaining a distributed database infrastructure is intricate, it's complex again. Operating databases at scale, exceedingly challenging without sophisticated management infrastructure, and to automate them and to manage the intricacies is complex. And that's where advancements in terms of autonomous computing is going to add significant value. And that's going to be the future. Let's talk of another dimension. As we move to the future of databases, several challenges awaits us. That's given. But we as engineers, we as database engineers, we as data engineers will have to solve for. What's going to increasingly happen and what's going to make them essential for us to contemplate and have strategic planning as we navigate through these challenges is in managing autonomy. How do we manage and adopt multimodal databases? How do we ensure that the latency in edge computing is minimized? How do we implement advanced security measures? And how do we mitigate sophisticated cyber attacks? Those would be my 5 areas of focus over the next few quarters, few years to come. In conclusion, there are several trends that's going to shape the tomorrow of databases, including artificial intelligence driven autonomous databases, advanced multimodal databases, data at the edge, managing enhanced privacy and security. These trends will address many challenges of today and pave the way for a more flexible, efficient, and a secure data landscape or secure database landscape. Companies like Yugabyte will continue to evolve and almost contribute to becoming a golden standard for how databases would eventually have to operate. And as we continue to generate and consume more data than ever, these technologies will be crucial in helping businesses manage their data efficiently for better decision making. If you are responsible for data strategy in your business, stay informed. The database landscape is constantly changing. Continuous learning and adaptation are essential for effectively scaling databases. And today, as we stand at the cusp of new era of database technologies, it's imperative for us not only to adopt these changes, but also to actively participate in shaping the future. How we can contribute to this evolution as individuals, as engineers, as organizations, and to help build a more secure, efficient, and flexible database for the future is the order of the day. Thank you very much.